of Malcon, so I hope you also had a similar experience. So today, the game plan is Chapter 6, which is line bundles. And what I want to do is start out with a maybe 10-minute quick refresher on vector bundles and what they are. So a vector bundle, so I have some bank V, and map pi to x, is a vector bundle if there exists the following pieces of data. So we have explicit maps from a cover, say u sub I, a cover of x, and then we have maps from pi inverse of u sub I to u sub I, and let's say vector bundle of rank R to C to the R. So these are called local charts. And then it has to obey some compatibility conditions, OBY, compatibility conditions. And these are PIs. So the idea is that if we are on two local charts, so the picture's sort of downstairs, here's UI, and then above UI, we have sort of a cylinder. This is UI across C to the R. This is UJ across C to the R. And what I want to do is, if I'm in the intersection here, so here's some point P and UI intersect UJ. On the one hand, there's a fiber over P, so here's pi inverse of P. Sitting in this chart, on the other hand, I have a pi inverse of P sitting inside this chart. And if I picked some point in the fiber here, I would like to know, how do I move over to here, right? So how do I translate between the fibers? Everybody's with me on this, right? So this is the idea. And then in order to do that, we define transition functions. So the data of the transition functions is the transition functions. So we have pi inverse of UI intersect UJ, and that can map, on the one hand, we have phi I restricted to the intersection, maps to my UI cross UI intersect UJ across CR, but we also have the phi J restricted to UI intersect UJ. And this maps to UI intersect UJ across C to the R. So the point is, and this is exactly moving back and forth between these two charts. So what I want to do is to go back and forth, and I'm going to have two maps. Here, this is going to be GJI. So the way that we're indexing these, and there's not a standard convention, this is the sort of input side, this is the output side. So here I'm on the phi chart, right? So I'm on the phi chart, and I want to go from the phi chart to the phi j chart. So this is my Gij that takes me from here to here. And similarly over here, I go from the j chart to the I chart. So this is Gij. And so what are these maps? These are exactly, in linear algebra, when you had to change, right? We teach our undergrad students in linear algebra that there's not a God-given basis for a vector space, that you have to sometimes, you might have one basis, you might have another basis, and you need a change of coordinates, right? So this is exactly what our undergraduate linear algebra students struggle with, and that's exactly what these are. These are just change of coordinate maps. And so the GIJs and GJI live in GLR of OX UI intersect UJ. So in other words, what this is a R by R matrix of regular functions on this chart, right? And it's invertible, which makes sense because, of course, if I compose these things, I should get, help me out, audience participation. I got to get the identity, right, when I run these things. So the GIJs, and they satisfy the compatibility conditions, compat TI, BI, that Gij is GJI inverse. And of course, if there's another open chart in the picture K, and I go from GI to k ui to uj to uk, it should be exactly what I get by composing things. So the composition condition is that if I go from GIK, so I go from chart I to chart K, and I go from chart K to chart J, that this is going to be the same thing as going from GIJ, and these are on the triple restriction, UI intersect UJ intersect UK. Everybody's with me on this, right? So this is the data of a vector bundle. And then the last thing I have, maybe I shoehorn it in up here, is a section. These are going to be key objects for us. So a section of a vector bundle, we've got this map pi that takes us from the larger space to the base space, and a section is going to be a map going backwards that gives me the identity on X. So a section is a map from X to pi, and so up to pi, X to V, such that if I take S composed to pi X, that I get the identity. Right? So I take a point. So in particular, what a section is going to do at this point here, this point is going to go to some point in the fiber over it, right? So that's what the section does. So sort of pictorially, if I had, here's the base was one-dimensional, X is one-dimensional, and my fibers were also one-dimensional. This is my V is locally, notice V locally looks like X cross, in this case just C, if it was a line. So a line bundle is a vector bundle where the vector space is dimension 1, and so a section is going to be something that looks like this. That's a section, right? So at each point P, it goes to a little point up there, right? Everybody's with me on this. Okay, so maybe I'm belaboring the obvious, but then we have the check data, or the data for Cartier. Notice Cartier divisor has local data, if you remember, UI, Fi, which satisfy that Fi, Fj, Ox, Ui, say Uj, star. Of course, this is exactly GL1, Ox, Ui, say Uj. So Cartier, the local data of Cartier divisor gives a line bundle. Right? You guys are all with me on this so far. So in particular, I want to say just a little bit more about this line bundle, about the divisor of sections. So in this case, a section of F element of Ox of D satisfies, we know, that div F plus D is greater than or equal to 0. So on U sub I, we have div of Fi Ui equals div F Ui plus div Fi restricted to Ui. And so this is going to be my D restricted to U sub I. So this is the sort of the picture that we saw before, where we have the divisor of a character was equal to the divisor, or the section of Ox of D was equal, gives us the divisor plus some other bit. So, and in particular, the point is that div 0 of a section of Oxd is going to be exactly of this form. And so if we let the vanishing locus, is going to satisfy if Sj is equal to Fj, then we get Gij of Sj is equal to Fj, Fi over Fj times Fjf, which is then just Fif equals Si. So you see everything fits together very nicely, and this is how why we use the terms line bundle and Cartier divisor oftentimes synonymously. So the who cares about this? So you might be saying, so this is always a question that you guys should be asking professors. Who cares about this whole setup? Why would we care? And the big reason, at least for me when I first learned about this, is that all of this setup of line bundles divisors is the way that we get maps from our abstract variety. So X is typically given to us as a bunch of open charts, right? So it's just like in when you're studying manifolds, that you don't really have a manifold given to you globally. You have a manifold as a bunch of open pieces and charts. But if you wanted to see it globally, the point is you'd like to map it into some space. And the point is that if W contained in gamma OX of D is base point free, I have to say what that is, which by definition divisor is base point free, D is base point free. Say, this is terrible. I'm going to shoehorn this in up here. Divisor D is base point free if for all points P element of X, there exists a section S element OX of D such that S of P is not equal to 0. So if you're familiar with Hartshorne, in the case when you don't have a line bundle, if you have an arbitrary sheaf, a sheaf is said to be generated by its global sections exactly if at each point there's some section that doesn't vanish at that point, right? And so this is exactly in the case of so base point free, when you're dealing with this is the same thing as generated by global sections if you're an invertible sheaf. So I guess this is for each P. The sections, of course, can be different at different points. So that's what it means to be base point free. And so base point free, then we get a map from X to P of omega dual and all maps to Pn. So every map, if you want to realize your object in a projective space, what you need to do is find a divisor that's base point free, and that gives a map. So the one question that you might ask is, and the idea, of course, so if I have some space of sections, this map is, I have some space of sections here, or subspace of the space of sections. So this map, if I have a basis here, say F1 through Fk, in fact, let's just so that this be a basis for W. If W is some subspace of this, then this map is going to be P goes to F1 of P through Fk of P. So this is how we map objects to projective space by using the sections of some subspace of a base point free divisor. The one thing that you might ask yourselves when you're first seeing this is, what the heck is this dual? Why is there a dual there, right? What the heck? And so the point is, this dual is coming from, why the dual? Is that we have these fibers. Oh, here's our point P, here's pi inverse of P, and I have some point V sub P in the fiber, right? And the point, you guys are with me here, right? So I have some section, I have some point. But the thing is that what I really need to do is I know that wherever this map P goes to, it's going to be some multiple of this, right? So this is like taking a basis element, right? So the point is that this P goes to some point over here, S of P, and we know that S of P is going to be equal to, because this is a one-dimensional thing, it's going to be some lambda P VP, right? So I can scale it by this. And so there's the function that sends to each S element of W, let's call this L of P. This is I get a functional that for each section, it sends it to this scalar multiple of the element there. So what is this thing giving me? This is giving me a linear functional on my space W, because it sends a section to this lambda P, right? And so that's S and W goes to this lambda P. This LP this is W dual. Right, so we have functional. So that's the reason that there's that weird dual there. All right, that was almost 20 minutes, which is way more than I wanted to take on this, but that means that I could just talk really fast, which would be terrible, right? So instead what I'm going to do is slow down. So definitions. So a divisor D is very ample. Exactly when this map from X to P of gamma H, gamma of OX D is a closed embedding. So this is what we want, right? We want something where we see all of X. And we've seen examples earlier where I don't have a very ample divisor and my variety doesn't have enough room to spread out, so it's going to some object which is not isomorphic to it. Ample if some power KD is very ample. Some K. And base point free if the corresponding map, if this map is base point free, which we've already defined. So the goal today, we have 4 points I want to do. So 6.1, D. So this was all away from the Toric case. So this is all, but I know that everyone was very diligent and read section 6.0 over the weekend. But just in case you didn't, now you got a turbo dose of 6.0. So everything else now, we're going to switch to the Toric context. So the first thing is natural. So D, element of pic of X, sigma. So we're going to now be looking at Cartier divisors or line bundles on our Toric variety. So when is it one of these things? Is I'm going to start abbreviating ample, very ample, and base point free. So when does it satisfy these things? And as you might guess, there's going to be nice conditions in terms of the combinatorial data for when our divisor satisfies these criteria. 6.2, if you remember, same thing. How does, and this is, pic of X sub P. P is coming from a polytope now, right? So how does D, how does P sub D, the polytope, remember if we have a divisor has an associated polytope, and the question is how does the polytope of D relate to the original polytope? 6.3, this will be after our coffee break, Neff and Mori counts. And finally, 6.4, intersection pairing of curves and divisors in the simplicial case. So we're a third of the way through, and all that we've done is outline the roadmap, so I want to get moving here. Any questions so far? Okay. One of the exercises that I really like, so if you're seeing this for the first time, which I know some folks are, this is a huge gulp, so you just, this is a lot to absorb. The exercise that I like best in 6.0 is writing down very carefully the transition functions for the Grassmannian and figuring out what's going on just for G24 or projectively G13. So I think that's an excellent exercise, fun to work through. It shows you how everything's working. Okay. Quickly recall that we had D with summation A row, D row. It's going to be Cartier. So this is for the purposes of today's talk. Then we also had P sub D, was the set of M, element M, R, such that inner product and we had gamma of OX D was direct sum, and element PD intersect M, chi M, A, B, C, and D by Cartier because Cartier, we know that there exists, for all sigma, element sigma, there exists M sigma such that inner product of M sigma U rho equals minus A rho. And this is on a particular sigma for all rho and little sigma of 1. Right? This is our local data. This is what we call local data. So that was the setup. And now our first theorem is proposition 6.1.1. So if our max cones are n-dimensional or n-dimensional, then D is base point free exactly when M sigma is an element of P sub D for all sigma and sigma of n. Plain English, for every maximal cone, I get local data, right? It's a Cartier divisor. I have local data. That local data gives me a lattice point. That lattice point has to lie inside the polytope of the divisor for every maximal cone. It's a very nice, clean criteria. Now, I think I'm only going to prove one direction of this. So I prove this one. Let's go this way. So if M sigma is in P sub D, remember, P sub D is right here. This is the definition of P sub D. So if you're, sometimes, I mean, you've had a whole weekend to forget things, right? So P sub D is right there. So if M sigma is in P sub D, that means exactly that chi M gives us a global section. Chi M sigma gives a global section. That's what this is, right? P sub D, these are our global sections, right? Global section. S, and we know that div S, div 0 of S, is equal to div chi of M sigma plus D. And what that means is that for P a point in sigma of 1, for all points P, well, I guess I can just write it this way. This says that M sigma U rho equals minus A rho. And this means that the support of div 0 of S misses U sigma. Remember what the support is. The point is that this was my local data, right? And the divisor of the chi m is exactly given by this, right? So divisor of chi m is given by this recipe, but D was equal to summation A rho D rho, right? And so the point is that because this is equal on the nose to this A rho, those guys cancel, right? And so I have no, this support of the section misses U sub sigma. Because this is true for all the rays in sigma 1, right? So I sort of, you can think of this as being, this is where I'm allowed to have poles, right? And the point is that because of this equality here, all those poles are erased, so this divisor completely misses U sub sigma, right? So that's one direction. The other direction you can read in book. Now, if this left you cold, and for me theorems usually are not so exciting until they are brought to life with an example. We're going to do a nice example right now. So if you were zoning out on the proof, well, the partial proof, you should wake up. So we're going to do a nice example. So this is example 6.1.2. So our good old friend, the Hirzebruch surface, H2. And we're going to label our rays. So the first thing I want you guys to do is help me out writing down the Cartier data. So we're going to compare two divisors, D2 and D2 plus D4 using this theorem. What's kind of interesting is it's going to turn out that these two divisors have the same piece of D. So it turns out that piece of D is the same for both of these, but one of them is base point free and one of them isn't. So this is interesting because it illustrates a kind of surprising fact. You guys with me on this? Let's do it. All right, so let's write down Cartier data for D2. D2 Cartier data. So I've got my cones. So on sigma 1, let's write it down, sigma 2, sigma 3, sigma 4. So on sigma 1, I need my, let's say M is equal to A, B. So on sigma 1, I need A, B to dot with my U2 and U3. So U2 is 0, 1. U3 is 1, 0. I need this to dot to what? So I need it to dot to D2, the divisor. This is for D2. D2 lives along here. And remember that the Cartier data is M of U row greater than or equal to minus A row. So I've got a minus A row. So I need, this is my ray for U2. So I need this dot this to be what? It's a minus A row. A row is 1. So I need this to, if I want, and I remember I want equality on that patch. So I want this to dot to I want the equality, right? I want M sigma U row to dot to minus, and A row is just 1, right? It's D2, has coefficient 1. So I need this dot this to be equal to minus 1. This is my minus A sub U2. And on this, my D2, of course, is not supported anywhere, so this has to be 0. You guys with me on this? Right? That's my local data. And so this says that B equals minus 1 and A equals 0. So my M sub sigma 1 is just the lattice point 0 comma minus 1. Everybody good to go? Okay. And now we keep going. So you guys got to help me out. We need some audience participation, and nobody wants to do it. But let's see, on sigma 2, my rays are U3, and I'm going to kind of cycle around. So U3 is this. I'm going to have 1, 0. And then U4 is 0, minus 1. And here I'll have AB. On sigma 3, I have 0, minus 1, and minus 1, comma 2. And finally on sigma 4, I have AB, minus 1, 2. And then we cycle back around to 0, 1. Right? So here, this is going to be, this is, on this one I need what? This is going to be, this dot this is 0, so that just says A is equal to 0. This dot this is also 0, so this is B equals 0. So I get M sigma 2, so 0, 0. Here we get sigma 3, 0, 1 is 0. 0 still. Now it's a little different though. Let's watch. So this says that this says B is equal to 0. And this says that minus A plus 2B is 0, but B is 0, so A is equal to 0. So M sigma 3 is also 0, 0. And finally, this last one, this is, says that 2B minus A is equal to 0, but this one, what is it over here? It's minus 1 again, right? So because we've looped back around, and for sigma 4 we do pick up a D2. So this says A, this dot this is equal to minus 1, which says that B equals minus 1. Guess everybody good to go on this? Guys in the back? All I'm doing here is on sigma 4. On sigma 4, I have some lattice point AB. And the condition is that my lattice point, when I dot it with this, has to be 0, because this would be D1. So that's this condition. But this, on D2, Our divisor was D2, so I have a minus A row, so that's a minus 1, so that's this. This says B equals minus 1, but if B equals minus 1, then that says, help me out. B was minus 1, but that says, but then over here, since B is minus 1, I get minus 2 minus A equals 0, so A has to be A equals minus 2. So what I get here, when I draw my little lattice points in, is I have M sigma 2 and sigma 3 are 0, 0. M sigma 1, this is M sigma 2, goes to M sigma 3, is 0, 0. M sigma 4 is minus 2 minus 1. And M01, M sigma 1 is 0 minus 1, is this. So I get this polytope here. So, somehow I flip things in my calculation. So when I'm looking at this, you know what? This computation is absolutely right for D2. The problem is that what I wanted to do was D4. So this is a correct computation. This is correct, but wrong divisor. So we want to do this for D4. So actually what I want to do is compare D4 with this. So exercise. Do this for D4. For D4, what you should get when you do, so this is good actually, you should, if you're bored, you should mimic this. So for D4, when you do this. Oh, okay, all right. So then, so for D4, what you get is you get exactly this picture. M2, M4, and M1. M3, M1, M4. Whereas when you do it for D2 plus D4, you get the following picture. M2 prime, M3 prime, M1 prime, and M4 prime. And this is your P sub D. And so both of these points don't lie in P sub D, and so this one is not base point free, and this one is base point free. And I think for me, what's interesting about this, so aside from the correct calculation, wrong divisor, the point though is that you might think, okay, this divisor in some sense is bigger than this one, right? So I've added some extra stuff, so I'm allowing myself to have more poles. So you might expect that in some sense that is very vague, that this is a better divisor than this one, right? You'd expect you're allowing more poles, you'd expect more sections, better behavior, you know, closer to being maybe very humble. But in fact, this one's not base point free, whereas this one is, even though they give you the same polytope. So this is interesting behavior, in my opinion. So, so that's time to switch gears. So I want to recall support functions. So remember, if I had some phi sub d, where d was equal to summation a rho d rho, we had a support function, this map topological space of a sigma to R, and we had phi sub d of some u rho was equal to minus a rho. So this is how it's defined on the rays of the fan, and it's cone-wise linear. So if you think about what this is, or pictorially, this is going to be some picture that looks like this. So I'm going to have my fan. So my fan sits up here, say in the plane, and this is maybe a port. Let's do the fan of P2. So for P2, I may have my fan that looks like this. Here's one ray, here's another ray, here's the ray in the background. This is supposed to be inside that point, right? So here's the fan of P2. And then I'm assigning, on each of my rays, I'm assigning this minus a rho. So for example, if I took, the divisor, if this is D1, D2, and D3, and I picked the divisor D1, I would be assigning on the ray for D1, I assign the value minus 1, right? So this would be A sub row 1 is minus 1, and then A row 2 equals A row 3 equals 0. So I'd assign a 0 here and a 0 here, and you can see this gives me, having pinned these vertices, since the support function is linear, this gives me a linear function. So on the one hand, I'm going to have a plane here that picks up these guys, right? So I have a plane that I won't be able to draw well, but the plane that goes through these 2 points in the origin, right? I have that plane. Over here I have an easy plane, right? Because these both lie at height 0, so I have a nice little flat roof here. So this is like flat roof here. Then I have this side of my tent going down here. You guys are all with me, right? And then I have another side of the tent over here. So I have another sort of side of my tent here. So what I have, Hal's attempt to draw the tent well. So I have a flat roof over here in the back, and then I have a tent like that and a tent like that. So there's my bad tent. Do you guys see this or not? So I've got a piecewise linear function, and this is like the center pole of my tent. I have a flat roof here, beveled roof, and beveled roof. And so the point is that we can visualize these support functions basically as sort of like tents, certainly in the case of two-dimensional picture there. So, so a definition. S contained in N sub R, a convex set, phi mapping S to R, a function is convex if phi of t u plus 1 minus t v is greater than or equal to t phi of u plus 1 minus t phi of v. U and v are in S. So the point is that this definition of convexity, which just says, well, it says what it says, right? So I have 2 points, then I have to have, this is sometimes called upper convex, right? So this point lies above the line. I can connect the line of the images, and then I have the image of the line in the sort of source space. And this tent function picture is going to say that basically this, notice this is this is actually an ample divisor, and we're going to see there's a nice connection between this notion of convexity and when we have base point free ample and very ample. So that's the theorem we're going to do right now. So let's come over here. So here's the theorem. So this notion of convexity of support functions turns out to translate very nicely into ampleness, very ampleness, and base point freeness. So theorem. So this is kind of the centerpiece of section 6.1. And the following equivalent. D is base point free. Or phi sub d. And that's sort of for d. So the local data is sitting inside this piece of D. Notice we actually saw this already over there. Phi sub D of U equals min. So there's a nice condition, characterization of the base point freeness condition in terms of support function. So base point free is exactly the same thing as having a convex support function. So again, seemingly abstract definition. In the case of a toric variety, it comes down to combinatorial, well, discrete geometric data that relates to your fan. So, and in addition, if sigma is complete, if also sigma is a complete fan, then these are also then equivalent to P sub D is convex hull of M sigma element of N. This set are verts of P sub D, and finally P sub D of U equals min M in P sub D of M comma U for all U in N R. All right. So that's the sort of signature theorem about base point freeness, and now we're going to switch to ampleness. By the way, for this particular example over here, there's a nice picture of tent functions on page 268. See picture of the tent functions, the support functions. So let me remind you, definition 2.2.17, that P is very ample if for all vertices, M sub I and P, we had this, the vertex cone was saturated. So, and then in 4.2.10, we had D sub P, which was summation. This was a polytope. We could look at this corresponding divisor, A sub F, D sub F. These are the interpointing normals. This is Cartier. Remember P is a set of M such that M comma UF greater than or equal to minus A sub F. So then we get a proposition which now is going to tell us about ampleness. So 6.1.10. D sub P is base point free and ample. And if dim P is greater than or equal, if dim P greater than or equal to 2, then K D sub P is very ample for all K greater than or equal to dim P minus 1. And finally, D sub P is very ample if and only if P is a very ample polytope. So the nice thing about this theorem, maybe I prove just the first part of this theorem. So the base point freeness, this just comes automatically from P sub D. P sub D, polytope of D sub P is equal to P. So remember, if I have a polytope, I get a divisor, right? Polytope gives me a divisor D sub P. If I then form the polytope of that divisor, that's just equal to my original polytope. So that gives me the space point free part. And then what I want to do is talk a little bit about the rest of the ampleness. So let's see. So let's see, 6.1.1 shows that D sub P is base point free. So this gives a map from X sub P. This is the internormal, remember, this is defined by the internormal fan, You can't see that. You guys, in fact, should be yelling at me. To some p of gamma of Ox. But we also have a map, right, from x of p intersect m, right? So this is the map, because it's space point free, we have a map from sort of our abstract toric variety in terms of the fan to this. But we also have a map, right, because we had a polytope, we have that we intersect the polytope with the lattice. That gives us a bunch of characters, and we have a map from here to here, right? So some point p just goes to pi of m1 p of mk p. And the question is, what's the relationship between these two, right? Here's some embedding that comes from the fan. This is an actual choice of a divisor, right? I've got a bunch of lattice points. So having those lattice points corresponds to a choice of a divisor. So what's the relation between these two? So the very ampleness is going to happen exactly when this and this are isomorphic. So when are those two equal is the question. So the point is, here's the key point. We know that isomorphism is a local condition, right? That's something that we can check on charts, right? Isomorphism is something we check on charts. So if we have an open cover, and we have an open cover of x sub p, is given by the vertex cones, right? So we have our nice open cover given by the u sub sigma sub v. This is a vertex cone dual. And when did we get something that was embedding here? So this is our open cover, and the condition was that, let's say sigma v, this was a vertex cone, dual of a vertex cone. And so the point was that we know that 2.1.8 x sub p intersect m intersect u sigma v check is just equal to spec of c of n p intersect m minus m sub I. So this was what what x looked like on this local patch, right? So it was exactly this. So d sub p is going to be very ample exactly when, as we said up here, x sub p is isomorphic to x sub p intersect m. And that's going to happen exactly when this u of sigma v check is isomorphic to this, right? If their local charts are equal, that's that. Then when is this happening? That's happening exactly when this thing is saturated, right? And that's exactly what happens when P is very ample. So the condition, at least the first part of this, or actually I guess I just was doing the last part. So I did this part, is that we get an embedding. So dP is a very ample divisor exactly when P is a very ample polytope. So what's great about this is exactly the way you'd like the definitions to line up. All right. So I think it would be good to do a couple more examples before we close up here. So I have a couple great examples. So we got one page left. We got 10 minutes, so that's not so bad. Maybe I skip some proofs here. So what is strict convexity? So strict convexity is going to mean it's convex and for all cones we get an equality here of the local data dotting with u being equal to the support function of u exactly when u is in sigma. And so what this means in plain English, this probably, if you recognize what this means geometrically, hats off to you, you should buy me a coffee. What this means is exactly that the only places where you have, if you have two adjacent cones, you actually can see the ridge line. So strict convexity, so if I had two adjacent cones, had some cone here, and it's the same plane crossing there, it's still convex underneath here, right? I have still have line of sight, but this is not strict convexity. So what I want for strict convexity is I want to see the ridge line of the tent. So every time I go from one cone to another, I want to actually bend. So what this says is that you can see all the ridge lines of your tent. And here, tent is your support function, right? So every time I cross a wall, I can see the ridge line. So that's what the strict convexity definition is. So theorem 6.1.14, if sigma is complete, D is ample, if and only if phi sub D is strictly convex. And if n is greater than or equal to 2 is the dimension of my polytope and D is ample, then KD is very ample for all k greater than or equal to n minus 1. And 6.1.15, if sigma is smooth and complete, then ample implies very ample. So I want to do one last example of how to determine ample divisors. So the idea is the following: how to find ample divisors. And the answer is if tau, let's do it up here. Suppose that tau is a wall. So a codimension 1, if the maximal cones of dimension n, this is a codimension 1 face. So now I have some picture that looks like this. Here's some m sigma. Here's my wall tau right here. And I have some m sigma prime. Maybe this isn't maybe this is not a simplicial cone. We've got a non-simplicial thing. Right, so here's a non-simplicial cone. So what I do is I pick rho prime and sigma prime, let's call it sigma prime of 1, not sigma of 1. So I pick a ray that's not in the intersection here. So I pick some ray over here. So I'm going to pick one of these two rays. You guys with me here? And what I want to do is I want to check this convexity condition sort of across this face, right? So to convexity, obviously I can check the convexity by checking it across the codimension 1 faces, right? That's all I have to check. So, and checking across the codimension 1 face, convexity is going to be a local condition, so I'm going to just check here. So I pick one of these two rays, and then we know that 6.1.14 says that D is ample exactly when, so I picked one of these U, let's say this is U rho prime right here. This has to be strictly greater than minus A rho prime. This is the wall, it's called the wall inequality. Right, so this is the strict convexity condition. And so let's do this. I want to do this for the Hirzebruch surface, and then we'll call it a morning. So let's figure out all the ample divisors on the Hirzebruch surface. So on the Hertzberg surface, we knew that, let's see, this is minus 1 comma r. We know that D3 and D4 is a basis for pick. And so I want to consider AD3 plus BD4. So I pick a general Cartier divisor, and I want to know conditions. I'm going to label it in a sec, yeah. This is the same labeling that we used before. So this is U1, you guys can't see, U1, U2, U3, U4. And I'm going to keep my cones the same. So this is sigma 1, sigma 2, sigma 3, and sigma 4. So same labeling as before. I want to know conditions on A and B for ample. And we know the Hertzberg is smooth, so this is amazing. What we're about to see is that we can, just from the geometry of the cone, give a complete characterization of what the very ample divisors are on the Hertzberg surface. It's great, right? It's just discrete geometry. So let's do it. So what the condition is, first off, let's write down our Cartier data. So the steps are going to be, first, let's write down Cartier data. And I'm going to do this one for you because we should work through it, but let's just, I'm going to write down M1, M2, M3, M4 are equal to minus A0, minus AB, RB, B, and 0, 0. Just as a quick refresher, if we did have to do this and work through it, what's this one? This one says on sigma 1, which is right here, we know that my A comma B on sigma 1, when I dot A comma B with 0, 1, and I got A comma B dot 1, 0, and my Cartier divisor, this is D2. There's no D2 involved here, so this one is just going to be equal to, this is going to, on the one hand, it's going to be B, but this has got to be the coefficient of, well, this is the B over here that's different from this B. You guys are with me, right? So maybe I should call these alpha beta, since I'm only doing one example, alpha beta. On the one hand, this is beta, but there is no D2, right? D2 is not part of this, so we have to have beta equals 0, right? And when you do the other one, you get, we get D3. So when we dot this thing, I get alpha. But we know that this is at A, and so alpha has to be equal to what? Plus, or is it plus A or minus A? Minus A, right? So we get exactly this, right? So that's how we get these, and we go through and do the rest, right? So there's our Cartier data, and now we just want to plug our Cartier data into these conditions, right? So we plug our Cartier data into these conditions. So I'm going to do the first one. So let's look at, we've got rays, we have our walls, right? I have to check wall 1, wall 2, wall 3, wall 4. So here's my 4 walls. So on U1, our Cartier data over here on sigma 3, I'm going to cross this wall. I'm going to pick RBB as my data here. So here's my RBB. This is my M3. And we know that M3, when I dot it with the ray on the opposite side of the wall, the ray on the opposite side of my wall is what? I'm crossing this wall, right? So I'm going to dot it with U2. You guys with me here? I'm dotting it with U2. And U2 is just, of course, 0, 1. So that's equal to B. And that has to be strictly greater than what? My minus A rho prime. What was the rho prime on this? What's the rho? I mean, not the rho. What's the coefficient of my D? 0, right? Because this is a D2. B greater than 0. So is everybody with me on this? So it's a very combinatorial thing, right? I take the thing, I cross a wall, I dot that divisor with this thing, and I compare it, and it has to be strictly bigger than the coefficient of the D. So when you cycle through the rest of this, we get 0, 0, minus A, 0, minus A, minus A positive B, So what do we get out of this? This one I get 0, this one I get 0, and this one I get A. So at the end of the day, this is, oops, this is not right, yeah. This would be A plus BR, right? So here I get B greater than 0, here I get another B greater than 0, here I get A greater than 0, and here I get this other condition. And you can see, what do I get? B has to be bigger than 0, A is greater than 0. This is superfluous if I've already got these ones. And so we get A, B greater than 0. And there it is. So now we've classified all the very ample divisors on a Hertzberg surface just by doing these simple, number one, writing down, you hand me a divisor, I write down you hand me a divisor, you write down the Cartier data, you do this little wall crossing check, gives you a bunch of inequalities, there's your criterion for very ampleness. So I apologize, I went a couple minutes over. I actually had another page that I wanted to get to, but this means that at the start of the next hour, we will see, using this sort of machinery of support functions, a smooth, complete toric threefold, which is not projective. So how would I prove that? What's the simplest way to prove that something is not projective? It has no very ample divisor. We just said at the very start, the reason we care about all this line bundle stuff is that any map from our variety to a projective space comes by looking at the global sections of a divisor. We know that a divisor is very ample exactly when you get in embedding, so if I have no very ample divisors, I can never map to a projective space. And so not everything that is sort of, smooth and complete is as nice a sort of variety as you want, but it doesn't embed in a projective space. So good place to end. Coffee.